Hello everyone, this is lecture 6 of PTRE 475575, well completions and advanced stimulation techniques. Last time, Tuesday, we got a little bit technical into the stability of the stress state. We started talking about, okay, we have infinite permutations, possibilities about the stress state for SV, SH max, SH mean, and pore pressure. How do I understand which of those infinite possibilities is possible to exist in the Earth subsurface? And we started talking about one way to constrain this range is by determining which stress states will be stable, in the sense that if you have a fault under those stress state conditions that is favorably oriented in any kind of way, in terms of orientation, angle, stress of the fault, and components, petrophysical components, etc., etc. All the relevant properties are in favor of that fault is basically on the brink of failing. If you put that fault in that under that stress state, it will automatically fail and will cause shear slippage, which is basically an earthquake. So we try to constrain that, and we use a technique that I really enjoy. I really like myself, the stress polygon. And the idea is that we use this equation, but anything inside this little polygon is stable. And everything outside is either unstable, possible but unstable, so it wouldn't exist, and or impossible. That means SH mean will be bigger than SH max, which violates Anderson's rule. So I want to be inside the polygon. And we said we only need one equation to draw the polygon. This equation, that is the Moore Coulomb failure criterion, which you learn in geomechanics. And the only variables that determine the size of the polygon is mu, the friction factor of the fault, and the pore pressure. If you change one of those, the polygon changes. So you need a new polygon for every different pore pressure, for every different mu. And we were at the point, I believe, I helped you draw this line. And what I did is that I said, let's simplify the situation a little bit and call this axis Y and this axis X. I did a stupid thing last time, and thank God I called it. I called the y-axis X and the y-axis, the x-axis Y. I mean, it could take place. I mean, the axis is whatever you label it to be. Normally, we call the vertical axis Y and the x-axis, the horizontal axis X. But it's generally what your convention is. If you call it Z, it would be Z. Hypothetically, you can do it such that X is the vertical axis and the Y is the. Just make sure that you're consistent with everything. So we name it in an easy way. We call the vertical axis Y and the horizontal axis X. And then we take this equation. And we said for normal faulting, S1 is SV, and S3 is SH mean. We said that equal to 3.12, which is this, at mu equals to 0.6. And then we multiply. Then we divided both sides by SV. And when we divided both sides by SV, it made this 1, it made this constant, it made this the x-axis, and it made this constant. So you have something like x is equal to 0.62, roughly speaking, blah, blah, blah. And I told you, if you are in Excel, just make 2 columns. One column will have x, always 0.62. And the other one will have y. And we said, Shamel was here and he said, from 0.62 to 1, which is 100% right, 100% correct. But I was saying, if you didn't know you have to do it this way, you can draw a much bigger line and then understand which part you need to cut. You can draw a line that is like this, and then cut the portion that doesn't fall into the normal faulting. Because remember, normal faulting is this part. Everything is this triangle. So the portion of the line that is in that triangle, that's the one that you need. So that is how you do the normal faulting. Now, I want to use the reverse faulting. Take this equation. What is S1 in reverse faulting? The answer is SH max minus PP divided by what is S3 in reverse faulting is SV minus PP equals to 3.12. Delete that, SV minus 3.12 PP. Clean it up. Divide by SV, 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 SV. So this becomes Y, what I have on Y-axis. This becomes a constant. This becomes 1. This becomes a constant. So I have something like Y is equal to 2.2017, I believe. Something like that. So it's an equation of Y equals a certain value, which basically is a horizontal line, this horizontal line. Now, if you are going to plot it in Excel, you are going to make a column that has X, that would be varying, and Y, that would be constant 2.2017 all the way down to 2.2017. Or the Y values would be the same. The X values should vary from 1, which is this, all the way to 2.2067. So you are varying from 1 to 2.2017. But say that you don't know that, you don't understand that, and you want to extend beyond what is in the reverse faulting, you can go from 0 to 3 if you want, and then you're going to know which part to cut. Like you're going to cut the part that is not in the reverse faulting region. And that's how you draw those 2 equations. So I have a line for normal faulting and a line for reverse faulting. Okay. And a line for reverse faulting. Now, I'm missing the last line. And if I want to cheat, I will take this point and this point and connect them together. I can do that. But let's not cheat. Okay? Let's do it for strike slip. And now strike slip is a little bit more complicated. It's not a vertical or a horizontal line. It's a slanted, sloped line. So it's a little bit more complicated equation. It's not Y equals something or X equals something. It's Y equals MX plus C, you know? Straight line. It's still a straight line, though. Don't get me wrong. I take this, bring it here for strike slip faulting. S1 is SH max. S3 is SH mean, equal to 3.12. Okay, I erase extra and I divide by SV again. This becomes Y. This becomes a constant. This becomes X. And this becomes a constant. So I have a Y equals something constant, X, plus something else constant. So it's an equation for a line Y equals Mx plus C. Okay, and then I go to Excel, 2 columns. One column X will start from 0.62 all the way to 1. And Y will start from 1 and will go all the way to 2.2017. And again, like I said before, I can draw a huge line. It would be like this. And then probably it's going to be a minus value, the intercept. But I can say, hey, this is only valid for strike slip faulting. So what is the strike slip faulting region of this plot? Is this region. So I need to cut this part and cut this part. So let me just very quickly, I think there is a student looking for me. Let me just tell him I'm in class. Okay, so this is how you draw it. And I give you the equations. It's basically exactly what I did. But this is how you draw the polygon. And then we have the region for normal faulting, strike slip, and reverse. And the counterintuitive thing is that there is a bigger range of stress states within reverse faulting that is stable in the Earth subsurface compared to strike slip and normal faulting. But in real life, if you see Jens-Erik Lund's-Knee maps that are colored a certain way based on the stress state, there is much more blue than other colors in the world in general, which means that it tells us that most of the red, there is much more blue and green than red, I would say, which tells you that most stress state in the Earth's subsurface are clustered around in this portion of the map, like sort of like that area, southwest corner of that stress polygon. That doesn't mean that you don't have reverse faulting. If you go to Australia, if you go to Nepal, if you go to east coast of the US, you will find reverse faulting. There are places within the Marcellus Shale, for instance, that are quite reverse faulting. So on and so forth. Now, taking it one step further, honoring what Jens-Erik Lund's-Knee did, where he used the Simpson equation for AFV, you can color the inside of the polygon with this color scheme. From dark blue, which is very normal, faulting stress state, to dark red, which is the very, very, very reverse faulting stress state, and everything else in between. what does a very, very normal stress state, faulting stress state means? Basically, SV is huge compared to SH max and SHP. And then you have, very, very normal faulting. I think it means that, SV is huge compared to SH max and SH mean. Then you are in the interface between reverse faulting and normal, where you have SV is equal to SH max, which is bigger, and they are both bigger than SH mean. Then you have the other interface. I'm talking about, first I was here, then I'm here. This is SV is huge compared to SH max, which is equal to SH mean. Here, SV is equal to SH max, and they are bigger than SH mean, both of them. Here, SH max is equal to SH mean. No, I believe, yeah, it's equal to SH mean, and they are bigger than SV. And then here, SH max is bigger than SH mean, which is equal to SV, something like that. But basically, you go from dark red is very reverse, dark blue is very, very normal, and everything else in between. All right, so how do we use the polygon? And I said, I believe that you guys know by now how to use the more Coulomb, more circle. And we can use it the same way, then stress polygon, the same way, the same exact way. Example problem number 5. Injection from saltwater disposal wells in the Fort Worth Basin is thought to be responsible for elevated seismic activity. Use the stress polygon concept to determine the validity of these concerns. The local pore pressure is thought to have increased due to SWD from 0.43 SV, hydrostatic, to 0.72 SV, and mu along the local pre-existing faults is assumed to be 0.6. The local SV is 7,000 psi, SH max is 6682 psi, and SH mean is 5345 psi. So how do you use the polygon for that? Before we do that, I want a little bit of background, is that, and I believe you already know what I'm gonna say, but I don't know the background of every student in the class. I know some of you pretty well, but some others I don't know. So let's just understand where this problem is coming from. So this is Texas, lad, I guess. And this is Barnett Shale. I'm drawing it black. And this is the original success story of the shale revolution of the US. George Mitchell, which we are going to talk about in module 3, this is where he made all of his money. When he thought about doing fracking, this is where he basically said there is this rock which is highly impermeable, like glass, but it's full of oil. How do I get this oil? Even if the rock is glass, highly impermeable. He said, okay, let's come here, put a rig, drill a well, fracture it, and then we are gonna get oil to flow up. And we have a ton of oil here. Gas. Gas is gonna be, gas is red. Now, we have this, but with it, we get a ton of water. A ton of water. Bigger than that. And guess what? Is salty water, nobody cares about it. It's not like we have people thirsty in Dallas, or we have issue with, there's not much we can do with that water. Okay, nothing we can do. Nothing useful to do with the water. So somebody comes and says, okay, what are we gonna do with this water? I mean, it's on us. So somebody comes and says, hey, you know, if you go beneath the Barnett, there is an aquifer called the Ellenberger Formation. And the aquifer is very, very porous and is filled with water that nobody really cares about too much. It's a very big formation. How about we come here, we drill another well, a smaller well, vertically down, and we will take this water that we produce and inject it down to the Ellenberg. Okay, we call that well, it's a saltwater disposal well, SWD well. For EPA is class 2. Okay, this was a class 1 well, ordinary well. This is class 1. Class 1 EPA. And this SWD is class 2 EPA. I don't know how long EPA will still exist, but this is how they call them. Class 6 is the carbon sequestration well, and there is others in between. But if you go to conferences, you may hear this term. That's why I want you to be familiar with them. I'm not gonna test you on this stuff. But anyway, they kept injecting for several years, like 16 years, 15 years in the same formation. And then suddenly, after several years of injecting, you start getting earthquakes in places you did not expect earthquakes before. And they kept going, like the earthquakes pile up. And really, you can feel the earthquakes that are above a magnitude of 3, but there is a bunch of them that are, they take place and you don't really feel them. And then eventually the earth is shaking. And a lot of discussion when I was a student about earthquakes in Fort Worth Base. Then there was discussion about earthquakes in Oklahoma. Then there was a discussion about earthquakes in Canada. And there was a little bit of a discussion about earthquakes in the Bakken, but Bakken is a little bit of another story. Ultimately, what happened is that when you are injecting, you are doing, what are you doing to the Ellenberger, the yellow Ellenberger? You are actually increasing its pore pressure. Okay, you are increasing its pore pressure. And then what will happen, you are gonna get to a point where this S1 minus PP divided by S3 minus PP, you want this to be stable. It's something, if you remember, mu plus square root of whatever. Okay, if this is the case, you are stable. But then you increase this P, this PP, and you get to a point where this is the case. And now you are in trouble because you can have a pre-existing fault here. If you increase the pore pressure, you are gonna make it slip. You make the fault slip. In shear, you have an earthquake. If you make a lot of faults, there are big faults, and you get a lot of earthquakes. And that's how the seismicity, induced seismicity, the term induced seismicity, very fashionable when I was young, when I was a young graduate student, came by. Oh, that's a terrible drawing. But that is the idea, class 2. But yeah, that's the idea here, is that we get a lot of salt water that we really don't care about, but we have to deal with it. And the answer is, hey, it's Ellenberger. We just dispose it in aquifers, but then earthquakes happen. And then people started blaming the frac jobs for the earthquakes. Back in my time, there was a big debate. They thought that it was from the frac jobs that the earthquakes are coming. No, it was from the associated saltwater disposal operations that the earthquakes were coming from. Okay, now how do I show it on the polygon? And it's step 1, I'm gonna build a polygon for the original conditions with PP over SV being 0.43, which is hydrostatic. And then I will build another polygon on the same plot for the new pore pressure. And I will use the same plot to show the difference. And if I had big audience, I would have asked, which polygon do you expect to be bigger, blue or red? And the correct answer is the red. You have first the blue polygon that is going to be big. Sorry, the blue polygon would be bigger, the original one, the initial conditions. Pore pressure decreases the size of the polygon, and then you get out of that. You find yourself outside of it in the unstable bounds. Then I will use green to add the local stress state. And if I'm right, the stress state will be inside the first polygon, but outside the second polygon, if I do it properly. And that's the case. Initially, at PP over SV equals 0.43, I have this polygon. So my stress state, this is the Fort Worth Basin by the Barnett, basically North Dallas, North Texas. I'm stable because I'm inside. The green dot is inside the blue polygon. But then as the pore pressure increases, and I find myself outside of the polygon, the polygon shrinks, and then the green dot is outside of the final polygon. Then I'm in trouble. That's when I get the earthquakes. Now, if I was using a more Coulomb, a more circle, how would it look like? The answer is sigma n tau. Now my envelope starts from 0, the origin, because I'm assuming that the rock is pre-fractured. We are dealing with large-scale rock, so I cannot have an intercept. I start from the origin. And then initially, I am here. Sorry. I am here. Sigma 1, sigma 3. And then with the increase of pore pressure, it gets shifted to the left. It stays the same size, but is shifted. I'm trying to draw them the same size. Sigma 1 prime, sigma 3 prime. I start from the right, and then I get on the left. Now I am cutting this part, the envelope. I am cutting the envelope, so I do have failure. It suggests that I have failure. Now, if I had drawn the circle, now imagine I have 2 polygons. The green line, the green line is inside the big, but outside of the small. if I have the green line touching, if the green dot was here exactly on the polygon, it will look like this on the touching at one point. I will be saying I'm at critical conditions. That means I'm just about to sleep. I'm just about. Not there yet, but it's on the very, very, just about to sleep. A lot of analysis that we do in class or in research involves this kind of critical condition. And that's when you basically expect the earthquakes to start. Doesn't mean that you're gonna feel all of them, but that's and they're artificial earthquakes. They are like induced seismicity. Any questions? Because I will switch the subtopic a little bit. Okay. So, also stop me if I am I'm going too fast. It's just because I believe, especially the undergrads for sure, but I don't know about the graduate students. If they have seen this stuff before, I mean, I can go faster. It's a little bit abstract, but if it's something that you are seeing for the first time and you want me to emphasize something, please let me know. Now, when I drill a well, I remove rock and I fill it with fluid. Basically, that's what I'm doing. I remove solid rock, replace it with fluid. So I'm disturbing the stress field around it. I create perturbation in the local stress state. So when I go near the well, I don't, this SVSH max SH mean is no longer valid when I'm near the well. They do play a role. We call them the far field stresses. They do play a role, but if I go next to the well, it doesn't mean that the stress field will be SVSH max SH mean. It will be something else that depends on other things, including SVSH max and SH mean. And then as I go away, the stress field becomes more and more SVSH max SH mean. Because the presence of the wellbore disturbs the surrounding stress field, basically. We call this the near wellbore stress state. And because of the shape of the well, I prefer to use cylindrical coordinates. So I go from Cartesian, which is x, y, z, as v, as max, as mean, to a cylindrical coordinate system, r, theta, and z, or polar coordinates. And now I have 4 new stresses that determine the stress field. I have radial, that I always use green in all my papers to signify radial. Tangential, I always use red in all my papers to signify that. Axial, which is, we call it sigma ZZ if it's aligned with the z-axis. It doesn't have to be the z-axis. It might be the x-axis or something, but anyway, blue, I always use blue. And the shear, which is sigma theta, I use purple, magenta color for it. Now, those stresses, they have their own equations, and these equations, they have SV, SH max, SH mean inside them, Poisson's ratio, etc., etc. So they do get affected by what stress the Earth applies on it from far away, but they are also affected by what happens inside the well. Because inside the well, you have something called pore pressure. And inside the rock, you have something called pore pressure. and something called Poisson's ratio. And then the distance that you are from the wellbore also matters, etc., etc. Now, the names of those new stresses, radial, tangential, axial, shear, dictate their orientation with spatial orientation, their orientation in space. So it doesn't really matter where you are. I mean, you can figure out the direction of the stresses just by telling you the names. I will show you how you can do it with some examples. Let's just say I am here. And I want you to give me the directions of the stresses here. I'm in the southwest side of the wellbore. I'm southwest of the wellbore. Close by, but not right on the wellbore. So I start from the center of the wellbore, and I draw a dotted line to that point. That's all I need to do. And then let me extend this line with a green arrow. This is gonna be sigma RR, the radial stress. The direction of the arrow depends if it's tensile or compressive. Now for beauty, I draw the arrow being compressive. Sorry, tensile. But it doesn't mean that it's tensile. It could be compressive. It could be like this. But you will see why I prefer to draw it just for beauty like this. Because now I'm gonna come perpendicular to the radial stress, draw another arrow like this at right angles. Put the arrows like this again in tension, and I will call this sigma theta theta, the tangential stress, also known as hoop stress. Okay, hoop stress. Hoop stress is a nickname. Circumferential stress is another name. Tangential stress is the official name. Now, it's drawn in whatever, tension. But what if it's sorry, guys. I apologize. It was one thing, so let me draw it again. I drew it in one move. So imagine if it was compression, it would be like this. But you know, it doesn't look very beautiful. Imagine if I had the green arrow in compression as well. It would look very messy. That's why I drew them in tension. And it doesn't matter what class you are taking. The orientation is the same. Now, whether you are taking solid mechanics and you have tension positive, or geomechanics and you have compression positive, it's going to affect where the arrows are pointing. Just that. So we did the radial, we did the tangential. Let's do the axial. The axial will be the direction of the wellbore. So I'm going to put a big cross here, which signifies an arrow going inside the plane of the screen. Okay? As I'm looking at the screen, I don't know if you can see me, inside, along the wellbore, parallel to the wellbore. Or the other way is if it's coming outside, it will be a dot coming out towards me, out of the screen that I'm looking at, coming this way. Okay. That's how those three stresses are, and those three are normal stresses. What about the shear stress? The shear stress is, I need to draw it with an element, a representative earth element, like, let me draw one. It should be like this because of the shape is affected because of the presence of the wellbore. It's no longer square, so it would be something like this. Okay. This is the direction of the stresses. Now, let me do it the same thing somewhere on the top, northwest side. So something like this. I start from the middle of the well, and I draw a dotted line, and I extend it with the red, with green ink, and that would be sigma RR, the radial stress. Perpendicular to it is the tangential stress, sigma theta theta. Along the wellbore, going in or out of the screen. In or out, the direction will be dependent on the value. If it's a negative value, it will be one way. If it's a positive value, it will be another way. It doesn't matter to you now, but the orientation is what matters. Okay, it goes parallel to the wellbore. That's what you want to know. And if the wellbore is said to be along the z-axis, it's gonna be called sigma zz. If the wellbore, I forgot to draw the sigma zz is blue. If the wellbore is set parallel to the y-axis, as I have some papers from my PhD, it's gonna be called sigma yy. If it's set along the x-axis, like Nassim is doing in his PhD, sigma xx, same thing. Some people say sigma ii, and no matter what that I direction is, it just needs to be the same component. And then, of course, I have the shear, sigma r theta. Here it's going to look like this. And again, the arrow's direction will depend on the value of the stress. Okay. Now, let me be a little bit tricky. I mean, we are wells people, right? We care about our wells. They are very important to us, so we care about the stresses on the borehole radius, on the wellbore walls. So let me draw the stresses at this point here, right on the borehole wall here. I will extend the line from the center of the, need to make it. I want it to be in black color. And then I extend it with green ink, sigma RR. I go perpendicular to it. And basically, I'm tangential to the well radius. I am basically sigma theta theta. I'm touching the wellbore circumference at one point only. Only a single point. It's like a tangent to the well. Sigma theta theta. And then I am doing the axial, which will be like this along the wellbore. Axial. Sigma zz, I'll be writing. And now you guys were going to ask me, what about sigma what about the shear, sigma r theta? And I will tell you, don't worry about the shear because it goes at 0 on the wellbore circumference. On the wellbore circumference, it becomes equal to 0. And then you're going to tell me how so, and I will tell you wait until we see the equations. I believe you have already seen the equations, but yeah. If you see the equations, you will see that it goes to 0 of the wellbore radius. So these are the stresses when you have the wellbore presence. Now, it becomes even more complicated if you have a perforation present, because think of a perforation as a secondary tunnel that is also filled with fluid and it's also under pressure. So it complicates the stress field quite a bit, quite a bit. This is how it looks like from an old paper of mine. This one has everything in compression except radial. Radial stress is in tension. Now, the history of that is people have spent a lot of time trying to come up with equations for those stresses, and we are going to see some of those later on. The first people to look at it was Lamé and Clapeyron. You may know Clapeyron from your thermodynamics class. Clapeyron equation for the vapor pressure with versus, is it vapor pressure versus pressure or vapor pressure versus temperature? I don't remember right now. And you know Lamé from geomechanics. Together in 1831, I believe they were working on cannons. How much you can load a cannon before it explodes? How much load you can put inside a cannon and do it so that you use them efficiently. And this is French people. They came up with the first version of equations that are really applicable to what they call thick-walled cylinders. And the cannons are thick-walled cylinders, and so are the casing of a well, etc., etc. Cylindrical coordinates. Then there was a German professor, I believe he was a mechanical engineering professor or a mechanics professor in 1898. And from my understanding, he was a theorist. And he took Lamé and Clapeyron and imagined a hypothetical problem of a 2D plate with a circular opening with stress applied on the opening, tension, the same way that you apply wellbore pressure, basically. And then you have one stress on one side, and you have another stress on the other side. So he did a completely conceptual analysis, and he modified, but he started from Lamé and Clapeyron, and he got into a certain stress field, a certain equations that were quite more, a little bit more practical if you have loading. And actually, I did it wrong. I wrote it would be what? It would be the same. It was uniaxial loading, not uniaxial loading. It was the same loading on any side, on both sides. So the stress on the top of the hole was the same as the stress on the side of the hole. Then there was somebody who probably modified those equations to make it a biaxial stress loading. You have a different stress on the top than a stress on the side. I don't know who that person is. And I ask other people, they don't know either. But somebody did it. Sadly, we don't get to know their name, and I don't know if it was one of the people that, maybe it was Kirsch himself, I don't know. But before I do that, 1913, somebody called Inglis took the same problem of Kirsch and make the whole elliptical. Applied ellipticity, basically. And Inglis is important because when we do fracture geometry, he appears again. Because the shape of the fracture is ellipse. His analysis actually is fundamental for the stress analysis inside a fracture, an open fracture. That's English. And then, by the way, so far, nobody's an oil and gas person, nobody's a geology person. None of them was Earth-related people. Lamech, Lapeyron, Kirsch, English, they had nothing to do with geology. Earth wasn't into play with when it came to those equations. Hubbard and Willis, Hubbard of the Hubbard's pig oil theory, 1 year after he came up with the pig oil theory, he was a geologist for Shell, and so was Willis as well. I know Hubbard went to University of Chicago, and he got his PhD fairly late, at the age of 34. It's considered late back then. It's still considered quite. I mean, yeah, you see a lot of people in their 30s doing grad school, and it's not a problem. I got my PhD at the age of 31, but I did 2 years military service before I started my undergrad. But anyway, Hubbard was working for Shell, and so did Willis. I forget his first name. I believe it's Mark Willis or something. And they wrote a beautiful paper that you can find in 1Pedro online. It's probably the best paper in SP's library. People claim that it's the best paper on petroleum engineering related paper ever written. Certainly the best of that century. And they took Kirsch equations, they applied pore pressure, static pore pressure loading, and they converted that to the equations that we use today. Now, what made this paper so great is the fact that, well, it was an excellent paper, very good work. It had analytical, mathematical portion and experimental portion, but also, if you go back to the 1950s and you go to an SP conference, something like that, or an AIME conference on petroleum, AIME is the parent organization of SPE. It was the American Institute of Mining, Metallurgical, and Petroleum Engineers. And SPE was part of that until 1957, I think it went off. And then 1985, it became completely independent. But that's irrelevant. What was happening back then, the rooms were divided into horizontals and verticals. People were arguing and they were saying, oh, all fractions are vertical. And others were saying all fractions are horizontal. And they both had evidence about it. And they were all arguing. And it was quite, must have been a spectacle. But Hubbard and Willis came in 1957 saying fractions can be either horizontal or vertical. It depends on the stresses on the wellbore walls. And he did one experiment to show a fraction becoming vertical, and another experiment in gelatin showing the fraction becoming horizontal. And basically, he settled that debate. And some people didn't believe him, and they were still arguing, writing discussions about it, about his work, saying that it's not good. And he destroyed them in a very flamboyant fashion. He must have been a very good speaker. And then, yeah, I mean, King Hubbard. It was very, it's more important. That paper is more important than the pig oil theory, believe it or not. It's more, the implications of it is so high. One day I was leaving Austin to go to the oil field, and I stopped at a place, and I stopped at the Dairy Queen, and I asked the lady working there, "What is this town called?" And he told me San Saba. And I was like, "I know this place from somewhere. I don't remember where." And I realized that's where he was born, San Saba, Texas. It came to me later, you know. And I believe he died in New York or something. Anyway, now a few years after Hubbard and Willis, we had two other scientists in University of Minnesota, not far away from here, Bezalel Haimson and Charles Fairhurst. And they further modified Hubbard and Willis equations for polar elasticity. And that means fluid motion in and out of the poles, and the poles increasing and decreasing in size accordingly. Now, you may know that University of Minnesota has a very famous rock mechanics group that has people with chemical engineering background in it, people with civil engineering background mechanical people, mining people, and so on and so forth. And Itasca Consulting Group that has the software Black that is used a lot in geomechanics. It belongs to University of Minnesota. And I have a student working on that, with that, the one I texted earlier, working on this software. Haimson and Fairhurst, I think, were the beginning of that group. And I saw Haimson in 2019 for the American Rock Mechanics Association conference symposium. It was in New York the year before COVID. And he's an older guy, you know. I don't know if he's still alive or not. I was at Arma last year. I didn't notice him, but I know that the early career keynote speech that in every symposium there is keynote speakers that they give a speech during a lunch time, and one of those speeches is a young professional, somebody with from less than 10 years after he got his PhD. He's a young professor or somebody doing very well in the industry, and they call that early keynote speech. From this year onwards, they are going to be calling it the Haimson early career keynote speech. He was very, very important for them. Bezalel Haimson. And the equations they came up with, we are using them. So, all right. So that's the story. The first two had nothing to do with geology. The last two had a lot to do with geology. So, but equations for those stresses are very, very important. Very, very important. So let's see them. Assume that it's a vertical well and taking the angle from SH max to be theta. So if I'm looking at the well, like I said before, this is the well, this is SH max, this is SH mean, SH max. The angle theta is like clockwise from SH max. So at theta equals 0, I'm in the direction of SH max. At theta equals 90, I'm in the direction of SH mean. Okay, clockwise angle. If I do that, if I assume that, this is the equation for the radial stress, tangential, axial, and shear. Now take this equation and tell me, what if I said R equals to RW, which means R equals to RW, I'm on the wellbore radius. Okay, this becomes 1, this becomes 1, this becomes 1. This becomes 1. This becomes 1, 1, 1. This becomes 1. This becomes 1, this becomes 1. So you have 1 plus 2 minus 3. What does that lead to? 0. That's why I said earlier, shear stresses go to 0 on the wellbore. On the wellbore radius. And I guess it was like, it sounded a little bit dry. But this is why. This is the mathematical explanation why. Now, what if we make R to be very, very big compared to RW? This will become 0. By the way, everything was becoming 1 when R equals RW. Now it's becoming 0. So this is 0. This is 0. This is 0. 0. 0. 0. 0. 0. 0. So as sigma ZZ becomes as V minus PP, which is the same as sigma V. Sigma R theta becomes basically SH mean minus SH max divided by 2 times sigma sine 2 theta, becomes, this goes away basically. And there are some simplification you can get. Sigma RR, those go away, and you end up with PW minus PP. So it becomes much, much clearer. And there are several simplifications you can make. But the most important one that I want you to understand physically what it means is what happens when you go away from the wellbore at a specific angle. This is how it looks like for theta equals 0. That means theta equals 0. I'm in the direction of SH max. So SH max SH mean. And then that's the student I was telling you about. Oh, they cannot see you there. They need to be here. But if you go away from SH max, if you go away from the wellbore in the direction of SH max, the stresses will simplify themselves, and you can do it mathematically to figure it out. It will become, your radial stress will become SH max, and your tangential stress will become SH mean. And you can understand that by drawing the configuration I mentioned in the previous slide. If I come here and I want the stresses here, this will be this will be the direction of sigma RR, which is in the same direction of SH max, right? So, and this is what you see here. Now I know whoever made those plots, they didn't use my color scheme. They use red for radial stress, but it becomes equals to sigma H max far away from the wellbore. And then remember that tangential stress is like this, in this direction. This is parallel to SH mean. So if I go away from the wellbore, the sigma theta theta become equal to SH mean, sigma H mean, right? So, and of course, sigma ZZ becomes sigma V, because that would be basically parallel to the wellbore. That is at theta equals 0, which is, I'm looking at the well parallel to SH mark on top of the hole, as I drew it here. Now, let me And you can use the equations from the previous slide to understand what I was saying. Now, let's imagine SH max SH mean. Now, if I'm at theta equals 90, I'm here. If I draw the stresses the way I did 2 slides ago or 3 slides ago, the radial stress will be in this direction, sigma RR. The tangential stress will be in this direction, sigma theta theta. The axial stress will be again in the parallel to the wellbore. So now the radial stress is parallel to SH mean. The tangential stress is parallel to SH max. So I'm expecting it to look, the sigma RR will become sigma H mean. The sigma theta theta will become sigma H max, the opposite of the plot that I have here. So let's see. That's how it looks like. It becomes, we're on the other side of the web. So this is what I'm showing you to make you understand that the near wellbore stresses, as you go far away from the wellbore, they become equal to the stresses, the far field stresses. But it's not the same as I move around the wellbore. It depends on the angle I'm looking at. If I'm at theta equals 0, it would be SH max would be 1, sigma H max would be one of the radial or tangential, and then the other one would be the other one. And then flipped for theta equals 90. And I think, Donald, any questions?
I'm good.
Okay. So yeah, I think that's a good point to stop the class, because next one we are gonna do some, we're gonna get into fractures and stuff. So I think that's a good point to stop. There won't be any lecture next Thursday. I will be in Houston. I will send an announcement, etc. And yeah, I will be I'll be gone, but I will see you all on Tuesday. So thank you very much and have a nice rest of your day. Thank you, Donald.
Thank you.